So I just, okay, hello everyone. So welcome to this afternoon's tutorials on quantum control, because we have an excellent speakers. We have invited 4 speakers. They are Professor Xiaobo Zhu from the University of Science and Technology of China. He's already here. And we have Dr. Andrea Rowe from Orange Quantum Systems. He will join us soon, I think. And then we have Xiang, who's also here from National University of Defense Technology, China. And also Professor Lingling from Northwestern Polytechnic University. And they will give lectures on the following topics, including superconducting quantum computing. Who's speaking? Quantum controlling software, quantum programming languages, and also quantum compilation. The first speaker, so I will have a very brief introduction to Professor Zhu. He got his PhD in 2003 from the Institute of Physics, Chinese Academy of Sciences. And currently he's a professor at the University of Science and Technology of China. And his team is very famous, I think, in constructing several types of quantum processors, especially the type called Zhu, which is composed of 66 functional qubits. They have achieved sampling tasks in about 6 orders of magnitude, more difficult than that of Google's Sycamore. So let's welcome Professor Zhu.
Okay. Yeah, I think I should share in the screen.
Yeah.
Okay, it works.
It's coming.
Yeah.
Yeah, good. You can see the slides.
Okay. Okay. Thanks, Yuxin. So I just, I think this is a little bit different talk from my previous talk. I think I would like to talk some basic information of the superconducting quantum computing, because I think the audience is not indeed doing research in this field. So the title is just superconducting quantum computing. And let me start from the basic element of the quantum computing. It's just, we call it a qubit, the superconducting qubit. In fact, as we all know, if we go to the microscopic range, it's not like the microscopic systems. It's quantized. You see, if there's an electronic surround atom, so you will see the energy level is quantized. So this is normal in the microscopic systems. But if we consider another question, if the system is not a microscopic system, but a macroscopic system, can the system follow the quantum rules? Yeah, the answer is yes. In fact, in very early times, there's an experiment show if we just made up a Juice Junction, it's just a microscope structure. The typical size is about 1 micrometer or larger. The atom is about 0.5 nanometer. It's about 10,000 larger than the atom systems. So if you see, even in such a large system, finally they succeed in finding the quantized behaviors. They just measured and found the energy level is quantized. So that means even this macroscopic systems, if we can lower down the noise, the temperature into a very extremely low level, we can still see the quantized behaviors in such kind of macroscopic systems. So that's give us an opportunity to realize a quantum bit by superconducting materials in a macroscopic scales, not like an atom or single molecule. Okay, this is the principle. Imagine if we using superconducting materials to organize to form a LC resonator. If we can lower down the noise and the temperature into an extremely low level, we will see this harmonic oscillator is just quantized. Its energy the energy level is equally, and we can see it's just like a quantum harmonic oscillator. But the harmonic oscillator is cannot be used as a qubit because we would like to choose two of them. Then two of them energy level to form the qubit. But in this case, all the energy splitting is equally. So they cannot we cannot choose two of them to act as a qubit. So we have to introduce another nonlinear element. This element we call it Juice Junction. It's quite similar to the semiconductor NP junction. PN junction. The NP junction, in fact, is it's just a nonlinear element in the whole circuit. But in fact, the Juice junction is also the nonlinear element in such kind of system. If we can introduce such nonlinear systems like a Juice junction, then we can naturally form not equally energy levels, but we can choose two of them as qubit systems. So we obtain qubit systems. So in this case, if you look at the basic element of a superconducting processor, you'll find, in fact, it is like that, quite simple. You see, this is a picture. Okay, sorry. So you see, this is the picture of our 4-qubit processor, and this is a diagram of the system. You will see in this system, it always include, for example, inductance, capacitor, and the Juice junction. Typically, we didn't have the resistance because resistance will introduce dissipation. And in this kind of system, because a single quantum is very weak, if there's a strong dissipation, will destroy the coherence properties of the systems. So typically, in such kind of processor, we didn't include in resistance. It's only inductance, capacitor, and the Juice junction. So let's give us a very brief idea. Is this system is very easy to scale up because we just made the inductance, capacitor, and the Juice junction, and we can use the semiconductor technicals like the microfabrication technicals. So finally, we can print a lot of qubit to the systems. So it's easy to scale up, and it looks like easy to control. But if we can see it, what we are doing, we are doing a quantum computing. It's totally different from the digital technicals of the classical computer. Classical computer, we don't need very high precision control of each signal. It's digital. You see, if we control a signal like 1 voltage as the high as 1 and 0 voltage as 0, even we have a 20% of error, we can still work because it's a digital processor. But in a quantum system, it's totally different. For quantum computing, naturally, we need ultra high precision of each qubit, like 99.9% or higher precisions of each qubit. Otherwise, we cannot really obtain any useful information. So this is a big challenge. So if we consider to control such kind of quantum processor with extremely high precision, that's extremely difficult. In this case, we need to do a lot of effort, like, is that okay?
Yes, I think I should mute the other participants.
Okay. Okay. In fact, we have to control a lot of issues, like we need to calibrate each control path, and we need to reduce the crosstalk, the state leakage, and we need to realize the simultaneous gate operations, and we need a very high readout efficiency. So a lot of issues we have to account. So why the arrow, the control precision is so important? Let's look at these pictures. In this picture, we will see the x-axis is limit error rate, and the y-axis is the number of the qubit. We will see this huge area. Even we have a lot of qubit, like 1 million qubit, but our control precision, our limit error is 0.1. That means 10% of the error. We'll see we still belong to the range of the classically simulatable. That means that can be easily simulated by a classic computer. That's easy to understand because each gate, if you have a 0.1 0.1 error rate, like you only have the fidelity of 90%. So if you operate the qubit with 10 times, it's roughly, we can say it's roughly 0.9 to 10 times. So that means the error is already larger than 0.5. So in this case, we will see after very few of the gate operations, the quantum information is already emerged to the noise environment. So in that case, we will see we only can simultaneously improve the gate of fidelity and also improve scale up more qubit. That's the only way we can escape from the classically simulatable range to go to so-called quantum advantage. Here, the quantum advantage means if we can calculate some problems, if calculate some things that is faster than the classic computer, so we can say we go to the quantum advantage. So that's why here we need not only improve the qubit number, but also to lower down the error rate, the gate error rate. That's the both sides of the quantum process. So I would like to say integrate more qubit is much more easier than to lower down the limiting error rate. So this is our first step. If we can go to quantum advantage, we have some chance to go to really near-term applications, because we know the quantum advantage problem is always most friendly problems to the quantum computer. It's somehow difficult to the classic computer, but it must be very, very friendly to the quantum computer, because this is either way to achieve the quantum advantage. So currently, even we have realized the quantum advantage, but that problem, the sampling problem, is not really, we don't think it's really useful for the real application problems. So we are still make effort to go to the near-term applications. Of course, in the future, because we have the error rate is lower than the error correction threshold, we have the chance to realize the error correction, and finally we can have a very high, very low error rate. Then we can go to a fault-tolerant quantum computer. That means the future, but maybe takes very long time, maybe 10 or 15 years later, we can really go to the fault-tolerant regime, the quantum computing. Okay, so now let's see what is the system looks like, the superconducting quantum qubit system looks like. In fact, there's the key elements is quantum computing process is made by superconducting materials, and using the microfabrication technicals, we can integrate a lot of qubit on it. And but this is not the only key part of this whole system. We have put the process into ultra low noise and ultra low temperature platform to keep the process working. And also we need a very good control hardware to control each qubit with very high precisions. And also we need very good control software systems. I will show why the control software systems is very important. So the quantum qubit control is not like the classic computer. As I said, classic computer is just a digital one. So you don't need to consider a lot of issues here in the classic system, but here you have to control it, consider it. For example, we need to control each of the qubit with very high precision. Our target typically is 99.9%. That means 0.99939. The error should be less than 0.0001. So because we are using a microwave pulse to control the system, that's very extremely challenging to control each of the qubit with such kind of precision. We need to control each pulse, the amplitude, the phase, and time frequency. And the most worst things is in the system, if you really want to control each qubit with such high precisions, you need a compensation, a lot of things like the crosstalk. For example, if you control the qubit 1, inevitably there's some small leakage, although it's very, very small, like maybe 10, like less than 1%, but in this kind of systems, it's a disaster. We have to make it less than 0.1%, then the qubit can really work well. And also in these systems, we will see each of qubit, you need control, you need to consider the history of the pulse. That's extremely challenging. that means if the history of the pulse is different, so we have to change the form of the control pulse by consider the history of the pulse. This is natural. This is natural in the quantum systems. We have to control that, consider that. So, and also for multi-qubit systems, we need arbitrary multi-channel quantum circuit. So in this case, it just means we need compensation, calibration, a lot of signal, and we need to put all the signal together. So in this case, we have to optimize all the things. Otherwise, we cannot really have a useful software. So that means in this kind of system is totally different from the the typical classical software of the classic computer. We need to consider a lot of optimized method to really control the system and to really achieve a high precision. Okay, so I think until now, if we control on the order of 100 or several hundred qubits, we developed a very good software. We can really optimize the speed, and we can really control each of the qubit, and we automatically calibration all each of the qubit, and finally we can obtain some useful result. And another important thing is we have to make such kind of processors. Again, this is not. We can use the microfabrication machines from the semiconductor industry, but the key problems in here, what we control is a single quantum. It's very weak. We have to control a lot of, we have to consider a lot of noise channels, and we have to stabilize all the parameters in such kind of samples, and we have to speed up the development of new samples. So we made up our clean room, and I think we upgrade a lot of times. Finally, we can achieve good quantum processors. And this is our processors. We start from very few qubits, like 5 qubits, and that time the coherence property. This is the most important parameter of the system. It's not only on the order of 5 microseconds, and until now we have going to 66 qubit, and we have 30 microseconds of each qubit. So of course, in the future, we would like to have a longer coherence time, more qubit. That's all we want to do in the future. Okay, at the same time, we have developed our ultra low noise and temperature platforms. We developed our own electronic devices, and we have a very good control precisions, and also it includes a lot of channels, and we have a very good DC bias source. And finally, we can control our qubit, use the software, and finally we can achieve some result. So for the qubit system, let's start from our 12 qubit systems, because this is the first one we can really control a lot of, I cannot say a lot of qubit, but it's not several qubit systems, and we can really control such kind of system with very high precisions. And that's I think that's the most important step towards large scale quantum computing. In this sample, we'll see the coherence property is already good, and we can control each of qubit. For each qubit, we introduce the control line, and we can feed the very high precision control signals. And for that kind of systems, we will see the single qubit gate fidelity is already quite good, but this one is not done by a simultaneous way. This is just one by one. I will see, because in this sample, we still have some bad crosstalk. This kind of things, cause we cannot operate the gate simultaneously with very high precisions. But later I will show by some key improvement, we can really operate all the qubits in simultaneously and obtain a good control gate fidelities. At that time, we also use the so-called non-adiabatic CD gate. In this kind of type of gate, the gate during time becomes short, but they may introduce some other errors, but use some optimized method. This is I think this is hard. We take a lot of time to really optimize such kind of system. Finally, we can have a duration time very short duration time gate, and with very high gate fidelities, like 99.5. Until now, the 2 qubit gate, if we can have 99.5% of the error rate, fidelity is still high numbers. And the most important thing is the during time of the gate is close to the ideal case. Here, the TS is the ideal case. Our gate time is only 1.25 times of the ideal case. Before this result, I think the best result is about 1.7%. In any case, in such kind of quantum systems, the coherent time is always limited the systems. So if we can shorten the gate operation duration time, that's very important. We will see in the later quantum supremacy and the quantum advantage experiments. All the group go to this kind of non-adiabatic way to shorten the gate duration time. Okay, in this sample, we also succeed at that time the largest entanglement in such kind of systems. We know the genuine entanglement, in fact, is also very important benchmarking for a large number of systems, because if we realize a genuine entanglement in such kind of systems, we need to control each qubit with very high precision. Before the 12 qubit result, we use a 10 qubit to demonstrate the largest entanglement at 2017. But at this sample, we are not using the standard gate. What we're using is a central bus in this sample. And we bring all the qubits into central bus, and all the qubits resonate together. So finally, they can go to entanglement, genuine entanglement state, Ghc state. That's what happened in the previous sample. But now, because we have already very good single bit and 2 qubit gate, we can use this kind of standard gate to generate the entanglement. One important thing is at that time, because we have a larger crosstalk, so we have to use a parallel optimized way to optimize the gate fidelities. That way means when we optimize, for example, the 2 qubit gate of Q8 and Q7, so we in fact not turn off all the other paths. We just include all the other paths crosstalk, but we just optimize this 2 qubit in situ, and finally we can have a chance to optimize the whole systems. In fact, finally we can have 12 qubit entanglement with a fidelity higher than 70%. I think it's even than the fidelity of the 10 qubit. The 10 qubit fidelity is about 56. So here we increase the number, but also we increase the fidelity is higher than 70%. Okay, we will see for the 12 qubit systems, it's just 1D chain, as this is a simple structure for such kind of qubit systems. So what we finally want to do is go to two-dimensional ladder structures, two-dimensional structures. So for that kind of things, the first step, what we think is we can do it step by step. From a 1D structure to a quasi 2D structure. So that's the first step we have tried. So in fact, in first generation of 12 qubit is 1 by 12. It's just connected by 1D chain, and then we go to a 2D ladder structures. That means 2 by 12. Then we go to for 24 qubit. So seems this looks like very big improvement, but in our processor structures, that's very challenging, because in this case, the crosstalk, the wiring, all the kind of issues become much more difficult, considering we have to keep each of the qubit with very high precision. So that's very challenging to that, even from 1D chain to a 2D ladder structures. So in the 2D ladder structure, because we also improve a little bit of the control precision, we can demonstrate a good quantum simulation, some quantum simulation behavior result, and that works well. And you can see this the experiment result and this is theoretical result. They in fact they coexistence with each other very quite good. Okay, we didn't stop at the closer to this structure, the ladder structure, for a long time. We really want to go to the really 2D structures, so we go to the 2-1. We go to a 62 qubit. So in the 2-1 processor, in fact, we designed 8 by 8. It's really 2D structures. So it adds up to 64 qubits, but 2 of them are not function. So finally, we have a 62 qubit on such kind of processors. And most importantly, in this sample, we can suppress the crosstalk, especially the DC crosstalk, to extremely low levels, like 0.01%. Then in this case, we can tune our energy level with very high precision. So we can really go to some very high precision quantum simulation experiments. So we finally show quantum works on 2D superconducting qubit systems, and you can see the more details you can find in the science paper in 2021. Okay, and we also show in this kind of system we can have a very good control of each qubit. We can programmably control the excitation of each qubit, and we show maximum interferometers in such kind of processors. Okay, but the Zhu one, we still have I think not small a microwave crosstalk, and that makes us cannot really have simultaneously gate operations in such kind of systems. So we cannot go to a so-called quantum advantage. And also in Zhu one, we didn't have a very good readout efficiency. So also we have to improve the readout efficiency. So we from Zhu one, we make quite a lot of time go to Zhu 2. That means we can really control the qubit. We can really operate the qubit simultaneously and with very high readout efficiency. So before I just talk about the quantum advantage, let me briefly show what's the quantum advantage problem, the random quantum circuit sampling problem. What is exactly what this problem is? In fact, this problem is like we can randomly running a lot of gate on each of the qubit, and after after several rounds of the several cycles of the random gate, finally we do a single sampling. We just performed a single shot readout to each of qubit. And by this way, if the system is not emerged to a noise, we can still see some distribution. So it's not totally noise. So that's the problem. If it's total noise, so there's no special distributions. So this is what happened. It's not what happened in this kind of random circuit quantum sampling problems. So as we know, in fact, in Google, Sigma already show such kind of advantage. Also, we call it supremacy in such kind of quantum sampling problems. But why we need to do it again? So in fact, you see, because we perform a lot of gate filing and sampling. So if to check if there's still some fidelity. So obviously, this is one of the best way to benchmark the performance of whole systems, because in this kind of systems, we perform a lot of gate and we sample it and to check if there's some fidelity. And also we have to say the demonstration of the quantum advantage is not a single shot of treatment. At the first paper, in Google's first paper, they said their task, if you're using the best class computer, it will take 10,000 years. But very recently, it's shown that maybe the class computer is already faster than the quantum computers. But we know the quantum computer, the performance of the quantum computer can increase exponentially, but the class computer is linear. So if we can improve the qubit number and the depth of the circuit a little bit, so that means the task difficulty of the task can be improved exponentially, and we can beat the class computer. But we can say until now the class computer is still developed a lot of new methods to solve this kind of problems, and there's a competing between the quantum computing and the class computing. So we say this is not a single shot achievement. We can improve the performance of the quantum computer as well, and finally I think as one day they will totally beat the class computer. So that's again, in order to demonstrate such a good performance, we need to consider this kind of issues again and check it very carefully. Like we always say, it's ultra high precision analog circuit. We need to consider a lot of issues. So the most important improvement in this system, first of all, is just we used a tunable coupler. For quite a long time, all the multi-qubit systems is using the so-called fixed coupling structure. Imagine there's a 2 qubit, they have a fixed coupling. So if we want detune, if we want stop the energy exchanging from this qubit to this qubit, so the only way is we detune the qubit frequency from each other, because the off resonance can keep such kind of energy exchange. But if we scale up the system to a large number of qubits, this kind of way is not work well. There's 2 reasons. First of all, it's a so-called frequency crowding problems, because the energy, the frequency range is only 2 gigahertz. So we cannot arrange a lot of qubits in such a narrow frequency range. So the frequency is too crowding. So so we cannot really tune all the qubits off with a relatively larger off resonance frequency. So this is the first problems. And also the second is this whatever you have really tuned in this 2 qubit on off resonance, even you tune in like 2 gigahertz or very large tune, still there's some residual coupling in this 2 qubit. This kind of residual coupling, if we are doing some some simple experiment, not with very high precision, that works, because maybe they introduce 0.5% of the error. But in this kind of advantage experiment, we need to lower down the limit error to extremely low levels. So this kind of error is disaster. So we have to remove the residual coupling strengths between these 2 qubit systems. So we developed the so-called tunable coupler technicals. In this case, we can in situ tune on and tune off the coupling strength between 2 qubits. And this kind of things is dynamically done in a very short time, like several nanoseconds. So that means we can fully control the coupling strength between the 2 qubits. By this way, we will see finally we can achieve a very good result. For example, from this picture, you will see this curve is showing the coupling strength between the 2 qubits, and see we can control from the 18 megahertz to minus 25 megahertz. And during this tuning range, the coherence time of 2 qubits is keep quite good. And also we will see in this case we can easily have a gate fidelity higher than 99.8%. That's good result. And also we developed a very good high fidelity readout signal technicals to simultaneously read out all the qubits. And finally, we'll see for the 0 state, we can have a higher than 99%. For the 1 state, we can have a fidelity higher than 94%. Okay, finally, we composed all of these technicals. We just integrate 66 qubit and 110 couplers. In fact, each of the couplers is just exact same as the qubit. So in fact, we totally control 176 qubit, and each qubit, we can for the data qubit of 66 qubit, we can have a very high control positions. So we start to demonstrate the quantum advantage by the randomized quantum circuit, and we very carefully tuning each of the qubit and each of the couplers. Finally, we have this kind of good result. We will see in our Juice Junction 2, almost all the key parameters is higher than the signal. For example, the final version we have involved 60 qubit, and the single bit gate is 0.14%, and the 2 qubit gate is roughly 0.6%, and the readout error is 2.3%, and the coherence time is roughly 30%. And finally, we can have 24 depths of the circuit, and we finally we put the classical computing time is still go to 10,000, on the order of 10,000 years. And more details, please refer to these two papers. Okay, so let me give a brief summary. In fact, now we are here, we succeeded in the quantum advantage. And I think the next step, the most important thing is one is a quantum error correction, and another one is if we can go to some near-term applications. But for the near-term applications, we not only need to improve the hardware of the systems, but also the software, because I think the algorithm and the hardware software is also the bottom problems of this kind of systems, because we can only run a very shallow circuit. In this case, even we have a very huge space, so we can only run very few times of the gate. So that's very challenging for the algorithm and the software. So we can see, we would like to, we hope if we can collaborate with not only the physicists, but also computer science, all the fields to really go to the near-term application. That's very important, I think. Okay, I need to thank a lot of groups here. I just list here, and also I would like to thank our teams, especially Jianwei Pan. He helped us to organize such good teams, and also he is very good at the multi-qubit systems entanglement. So a lot of original ideas coming from him, and also Chen Zhipeng, he helped us to make up the electronic systems, and Chaoyang Lu, he's very familiar with the multi-qubit entanglement. So thank you for your attentions.
Okay, thank Xiaobo for the very nice talk. Since we still have 3 minutes left, I think we can pick maybe a couple of questions from the audience. By the way, I have just one question, because now you have Zhuzhongzhi 2. So your next milestone should be Zhuzhongzhi 3, I guess. So we look forward to see that.
Okay, thank you.
How many qubits are you going to set up for that?
I think at least more than 100. That's our
100, yeah.
yeah, that's target. And also, because IBM always they didn't describe the two types of qubit. For here, each coupler in fact is a qubit. In fact, the only difference is there's no readout signal or readout circuit in such kind of things. What we have control now, in fact, is 176 qubit. IBM claim they have 127 qubit systems, right? But they cannot realize a quantum advantage in that systems, because not all their qubits can have such high fidelities. So they in fact finally their target is just to use several qubits to work as a good qubit. So maybe we will change the claim a little bit, because in fact, if you look at the diagram of the coupler, it's just exactly same as a qubit, so that's it.
I see. Okay, good. Okay, excellent. Any question from the audience? No? Okay, if there's no question, so let's thank Xiaobo again.
Okay, thank you.
Okay, thanks. Now we're going to move to the next speaker, next talk. Next one is Adriaan. Yeah, you're here, right?
Yes, thank you.
Oh, good, excellent. Okay, so let me first have a very brief introduction to Adriaan. Adriaan, so he received his PhD from Delft University of Technology. That means that's QTech. And then he has done very excellent work, I think, on quantum control. And he has received a Zurich Instruments Pioneer Award. And then after his PhD, he started his own company. It's called Orange Quantum Systems. It is a company building diagnostic systems for GPU characterization. I think you're going to talk about that, I guess. Now, okay, Let's welcome Andrea.
Thank you very much.
Okay, you're
Let
welcome.
me see if I can share the screen. So let's see. Can you all see my screen now?
Yeah, I can see that.
Very good. Good. Oh wait, I could try to. Yes. So thank you very much for the invitation, first of all, for this speakers conference. So when I was asked to give a tutorial on this conference, I was asked to give it specifically about Quantifer, and that's an open source framework that we're developing together with another company, but also with the community to serve as the framework to control all of these experiments. So first of all, trying to introduce a bit what we are doing and how it all fits in. And then I hope to give it more as a tutorial than as a traditional scientific talk. And I think that means that I've also prepared several live demos, and I hope that you will appreciate these. So to start with, I think all of us are here to some extent because quantum computing is becoming a reality. I've put some of the world's first milestones of the last couple of years out here. And obviously in the previous talk, we saw some of the excellent results that were achieved in China that really take this to a next level. But I think one of the problems that we're seeing is that quantum computers are not yet realizing their potential. And this is a paper by Lewinsky et al. Where they said, well, let's try to have all the cloud accessible systems and run the same volumetric benchmarks against them. And basically what we're seeing is that none of them are really up to specs. And I think also was a little bit in the last talk, the relation to tunable couplers missing in some of these systems. But I think the overall point still stands. And if we then go to a high level, I think you can summarize it as there being three main challenges in realizing this useful quantum computing or this quantum advantage. We need to have some quantum application, preferably already in the NISQ era, where we do not have fault-tolerant quantum computers that can run arbitrarily deep quantum circuits. There's a big challenge on system integration, the chip architecture, the I/O, everything related to that. But the one that I like to focus on is quantum chip development, because we believe that the quantum chip is really at the heart of it. But I'm not much of a fabrication expert. Instead, I'm an experimental physicist, and I like to measure these systems. So what we need is we need to establish a fast feedback cycle to improve these chips. And there's a few things why this is different than sort of how testing in traditional semicon chips works. But it basically boils down to the fact that to test a quantum chip, you need to actually build a full quantum computer, consisting both of the test hardware, the full cryogenic systems, as well as all the calibration and tune-up protocols. To make matters more complex, there's actually a bit of a trade-off here, because we're always talking about we want to go faster, we want to automate it, we want higher throughput. But the moment that you're doing that, you're actually losing flexibility. So the moment that you're still trying out new control schemes, when you're still adding, let's say, should we use fluxoniums or transmon qubits? Are we going to put in a tunable coupler? What kind of design are we going to have? At that point, you want to be highly flexible and really be able to define your own protocols, prototype it, and really, have all the flexibility. And that also requires a PhD level operator. So that's up here, if you can see my cursor. If you're doing that a lot and you're doing the kind of experiments that we just saw, you need to move to, first of all, standardizing how you do it. If you're not doing like 1 or 5 qubits, doing it sort of by hand is not feasible, but you really need to standardize what you're doing. Going beyond that, you need to completely automate it, which also means that sort of the skill level of your lab operator should be able to, you should not require a PhD for that anymore, although in the current systems that might still be the case. And if we're really talking about high throughput, you want to optimize them. So here you need a typical lab setup and a software framework. And this is where Quantifer, which I'll be talking about, comes in. Then once you go beyond that, you want to have a standardized hardware setup, standard experiment libraries. But the constraint is that it only works for similar devices. You need to settle on, you can only make this for one kind of device, because you're trading off flexibility. Going to the automated, it's to some extent no longer possible to do this if you have only the hardware system, simply because it's always in use. So you need to develop advanced simulators, emulators also to develop against. And if you're going to this optimized stage, you really want to rethink your hardware architecture as well and say what the goal is. And that's the point where really a quantum computer starts to diverge from a test system. Now, what I'll be focusing on today is predominantly on the Quantifer framework. So why did we develop Quantifer? I think that if we're looking at quantum computing, whenever people are talking about software, there's an awful lot of focus on the applications. And this has resulted in a very wide set of publicly available open source frameworks. These are the ones I'm most familiar with, which might be a bit my personal bias, but there's quite a lot. They're quite mature, they're quite well maintained. So this is pretty excellent and great. But if we're looking at what we're trying to do when we're making this hardware, we'll realize that there's something missing. This is pretty much a top-down focus, and all the complexity of the experimental physics is hidden behind the interface. It's treated as a detail of the control electronics. What I'd like to point out here is that actually what's going on is we're missing a layer here. And this is the layer where experimental physics takes place. That's the layer where we say, hey, this is really where some tools are missing. Because the tools either assume you're going to be programming an FPGA directly, or they go to the high-level abstraction where you lose all the power. I'm hearing something from Yuxin, I think. Is there a question?
No, I think there's some noise. I'm going to mute those who.
Then I will move on.
Yeah, I think it's better now.
Thank you. So we developed Quantifer as an open source framework for solid-state physics that addresses these problems. We did this in collaboration with Qblocks, another company from the Delft ecosystem in the Netherlands that makes control electronics. And it consists of two parts. We have Quantifer Core, which contains all the basics for running experiments. So you have a data acquisition loop, live visualization, data storage, instrument management, everything to run basic stuff. But where it gets really interesting, I think, and this is really also where I think we're doing something novel and different from most of the things out there, is a Quantifer scheduler. It is control electronics hardware abstract. We have backends for both Qblocks, Zurich instruments, currently also working on supporting a Keysight backend. But the most interesting part is that we allow a really interesting way to sort of seamlessly mix and match the quantum circuit layer abstraction with a quantum device layer abstraction, where we're allowing users to express pulses and acquisition protocols directly. I'll go into that a bit more detail in a bit. So let me start with what Quantifer Core is. So it's based around a minimal set of concepts that if you understand those, you should be able to do everything related. And the first part is instruments and parameters, and we're inheriting these concepts from Q codes. This is a widely established framework for controlling experiments in the lab. What you can see here is basically a screenshot of the instrument monitor that we added that shows all the parameters of all the instruments. And here I've chosen to highlight a transmon device element that contains the parameters for the calibrated pulses. The other part is then the measurement control and the settables and gettables. So what this is that every acquisition we're doing basically consists of, on the abstract level, of we're setting something and then we're acquiring or getting something else. The way the measurement control is set up, here you see a bit of an advanced example. We're saying we want to vary this parameter X and parameter Y. So you can see here in the live visualization coming in, and we want to run, in this case, in Nelder-Mead optimization. We're saying, well, what's the adaptive function we want to use, and what are the arguments to pass to this particular method? And then we're running a minimizer on it. I'll be showing you a live demo of this in a bit, but this example is here just to highlight that this is possible. For data storage, we've also really redone that. We're basing this on the X-array framework, which is allowing arbitrary labeled multidimensional data sets. And it's a very powerful framework used in the data science communities. And we have built-in analysis class, and here you can see some examples. There's a tutorial on how you should make your own, taking care of the standard things like data fitting, storing quantities of interest, storing standard figures. And here you see, for instance, a resonator fit. I think the coolest thing I wanted to show, and I think that's something that really is part of why we did this, is the tutorials. So part of the things we realized was that everything that's out there is mostly developed in the academic world. That's also where our background is from. And here we wanted to make something that we sort of could use as a stepping stone. So I want to show you quickly the documentation of Quantifi. And I've prepared a demo, as I said. So I go here. And what you can see here is essentially that we have a pretty extensive user guide where we explain all the basic concepts I just glossed over. But the coolest thing, I think, is also here the tutorials. So the tutorial that I'll be showing you in a bit is how to control a basic experiment using the measurement control. And you can download these as an IPython notebook and then run them. There's a bunch more. One showing, for instance, the adaptive measurements in the advanced tutorial, how to build a custom analysis class. I see that adaptive is in tutorial 4 and not in 2, and how the live visualization works. I downloaded this before, so I can now show you this live demo. So I already connected to the instruments before we started the demo. So let me put this out there. So what we're going to be doing is, let's see, I think this might be a slightly better way to show it. I'm going to put this next to the tutorial text. So, and I hope everyone can still read it. So basically here we're explaining sort of what the basic concepts are, what the measurement control is, how we connect to the instruments. And the first thing we do here is we specify the data directory. So this is where the data will be stored. And here we're connecting to the measurement control, to live visualization. And we're going to be creating a so-called mock cosine instrument. This is not a real instrument, but just something that gives us a nice cosine, and we can control the parameters of it. And here we're displaying the source code of it. So here you also see that same piece of code and how it works, but here you have more explanation around it. Next, we're going to be doing a 1D loop around it. Again, these examples are sort of almost trivially simple, but I still think they're nice. So this one's kind of instant, and we see here what it's doing. I can also show you here, this is the live visualization. There's some details in there. You see this persistence mode, that's very useful if you're repeating an experiment multiple times. We get here the data set, and we can see the metadata like time, units, etc. You'll also notice that here it's telling seconds, here millivolts. But if you look here carefully, you notice this is in volt, because this visualization here is unit aware. So you see here now it goes to volts, and if I zoom out even further, it'll probably go to kilovolts, and I can auto-fit it again. Now I can make it a bit slower. This is a longer measurement. Sorry, I put the delay parameter. So let me see what the name was. I can look here also all the parameters. Acquisition delay, it's called. If I put this to this, for instance, we can now see that data is coming in real time. This is particularly useful when you're doing real experiments, such as, for instance, a spectroscopy experiment or the 4-hour-long Nelder-Mead optimization of your 2-qubit gate that was referenced before. I could go show you more. Here you see the default analysis for this particular thing. We're having here a 2D measurement, which is say first parameter, second parameter, set the points on the grid, the times and amplitude you want to measure, the thing you want to measure, and then you say you run it. I will not go over all of these in detail because we are limited. Here we can say how you do data that's not on a grid. You can also do more than 2 parameters, all that stuff. It's supported by default, and these are also concepts we've been using for a very long time in the academic world. We just re-implement and build everything from scratch. So going back to the presentation. First of all, are there any questions so far? If there are none, then I will move on. So I think what I showed you until now was fairly trivial and standard, but this is just the basic concept we're building on. Where it gets interesting, I think, is if we're talking about the quantum circuit diagrams, because then we're really entering the space of quantum computing. And the way that most of us have learned this is by reading Nielsen and Xiang and learning about the quantum circuit diagrams and the standard gates. And it's great for most quantum algorithms. Variation algorithms are a bit more challenging because you need to reinterpret some of the ideas a bit, but it's completely unsuitable for characterization and calibration. In fact, for most experimental physics, we're actually talking about pulses or the signals we apply to our device. And we need really precise timing control. Typically at the nanosecond resolution is kind of what we're thinking in the circuit QED community. This is kind of interesting because sort of the computer engineering way of thinking about this, where we're talking about clock cycles, is not the same units as physicists think about. And also how we're then putting things with barrier instructions and weight instructions is also a bit of unnatural to work with. Furthermore, we're applying our signals to ports on the chip and not to qubits, because these are abstract mathematical entities. We could, of course, say, well, then you just use that lower level of abstraction. But in many protocols, we actually require mixing these descriptions. For instance, one of the examples we like to use here is the so-called chevron experiment, a very common experiment where you're having quantum gates and in the middle, you're varying the parameter of a square pulse. Clearly, this experiment should not be expressed completely at the quantum circuit level because the operation in the middle is not a quantum gate in its traditional sense. But using everything at the pulse level abstraction is also very convenient. So what we use is we use a very traditional abstraction layering. We have a quantum circuit layer, quantum device layer, and then it compiles down to the hardware. Information comes in from different configuration files, and we can compile to the different hardware. So this is all fairly standard. But where it becomes interesting is that this layer here is sort of, you see that I've drawn one box. That's on purpose, because we're going to make a small modification to this that allows us to combine these two things. So we have the quantum circuit layer, where the thing that matters is the order of the operations. And we typically have things like gates and measurements that act on qubits. In the quantum device layer, the thing that's important is the timing of the operations. Are things exactly simultaneous? Is there a fixed amount of nanoseconds between this and this operation and something happening or not happening in the middle? These kind of constraints. And we're having pulse and acquisition protocols that act on a physical location on the device, a port, and are applied at a specific frequency that we call a clock. We're calling it a clock because it also contains phase information, but that's a technical detail here. And the realization we made is actually both these gates and these pulses, they're different representations of the same operation, the same conceptual thing we're trying to do. And if you're specifying the timing, you're also specifying the order. That allows us to combine these things into the schedule data structure. And this is where quantified scheduler comes in, deals with all this compilation. And here I also want to show you a briefly quick demo where we're seeing this compilation. And before I do that, I also have a third one prepared. So I need to know a little bit how much time I have left, whether I need to rush.
20 minutes?
25.
25.
25, actually,
That
because
is great.
Professor
Then-
Zhu ends earlier.
Excellent. Then I will gladly use that extra time. So we just released version 0.9 yesterday, which is a very exciting improvement on the compilation backend. And similar to Quantifer Core, we again have a user guide where we're explaining the basic concepts, the hierarchies, the scheduled operation. You can see also all of the figures that I use in my presentation here. But what's interesting is the tutorials. I'm going to skip the two basic ones because for this format, I can do them justice to some extent anyways. But what I can do is I can show you where is my, there's my Jupyter Lab. Very well, so tutorial 2, I'm going to give gates, measurement, and qubits. So what I'm going to show here is effectively, we're going to make a little quantum circuit and we're going to see that we add these operations and a bit of how to compile it. Yeah, let's go do it. So what we're doing here is we're creating effectively a very simple circuit. We're importing from our gate library the conditional phase gate to measure the reset and X90. Use this to create a schedule. And we can say, okay, that's cool. These are just the operations. There's the Rxy operation. This is a very important one because this is actually the native operation supporting these systems. And we can specify the rotation angle, the gate, and the phase. So this is another one. Again, we're following what I'm doing here, where we're explaining what is done. So here you can read along with what we're doing. And then going on. What we're going to do here, this I think is where it becomes really interesting, is now we're going to combine these ingredients to create a circuit to do a Bell state measurement. And I think this is where it becomes interesting because here we're really starting to see how the interface works. So we're instantiating here an empty schedule, which we give a name. That is a Bell experiment, one of the most standard things you can do in a 2-qubit experiment, consisting of first we initialize the qubits, then we add 2 gates, and we want these two to be simultaneous. So we put here the reference point, not as the end of the previous operation, but the start. That's sort of the default scheduling when you're not specifying timings. You can modify these kind of things. At the C phase gate, at the recovery gate, and then we're adding the measurement. So I create that, and I can also rely on the built-in plotting, and we're making a little limitation, change to the X limits, because to measure the Bell violations, you change the rotation angle of the final gate, as you can see here. And we're changing here that we're sort of not plotting all of it, but we're changing to only plot sort of 2 instances of the circuit. This is the for loop you see here of 21 of them. So this is all built in, kind of cool. If I would call this line, I would get an exception. And maybe I should show it. I think this one also shows it. And the exception is giving is that, hey, you're trying to now give the pulse of the specific explicit timings, the other one's the pulse level representation, where this information has not yet been determined. So what we need to do is we need to supply this configuration. And here we're loading one of the example configurations. That's for transmon qubits to compile it. Here's some more part. I think it's all explained here in the tutorial, what these cells are, where we're saying, okay, what information is in there, what's the structure of it. I can also maybe on this side show that all of these things are documented. So I can go here to device configuration. It will take me there. It will tell us what the data structure is, what it's used for, what elements it needs, what objects then specify the parts inside. There's an example in there. So all of these things you can read on, and they're there. And I think here, this is interesting. This is the timing table. So here you can see for every operation in your schedule, after you've done this compilation step, what's the start time, what's the duration, all the relevant information. And we can also, again, make a visualization using matplotlib. We also have a backend using plotly, but I think usually the matplotlib one is a bit simpler to read. And I'm not really sure why that one is hanging out. The output's already there. It looks like strange. That's the thing with live demos, of course. Let me quickly hit the stop button. So the keyword interrupt comes through. Good. I think that's because I already ran these cells before I went into the demo. And here you can see also again the circle diagram with some compilation added. And here it closes everything up. And this is then what you get out. So that is just showing the basic compilation, how you would sort it. Again, and this is why I asked how much time do I have left. These are just the building blocks we're using. And when it gets interesting,
19
minutes, that is perfect. Thank you, Xiang. Is when you put everything together. So I mentioned previously that Quantifer Core used the concept of settables and gettables, where the gettable is the thing that we're measuring, and the settable in this case would be the parameters of the schedule that we are changing. Now, every time that the gettable acquires data, this information is passed to generate a schedule, and this can also be a schedule containing multiple data points at once. And that's being passed to the compilation. We can also have here a settable that changes parameters in this config, so that if something changes, that's actually updated in the compilation process. And that gives us a compiled schedule. This goes to our hardware abstraction layer, which hands over the information to the relevant physical instruments that execute the experiment. And what comes back is a data set. And from there, we can take it back. Now, in practice, as a code example, I put an example of spectroscopy. Reason being that spectroscopy is typically one of these examples that doesn't play so nice with traditional circuit level compilation. So we have here the heterodyne spectroscopy schedule. And we add here a square pulse and the single sideband integration. So both at the quantum device level. And then here, again, the timing constraints. I explained them also in the tutorial. Then we want to vary the parameters. So what we do here is we say, okay, we define on top here 2 manual parameters that track this, and they go to arguments into this schedule gettable. I think this is a previous version because we now have a generalized schedule gettable. And they're interpreted to be evaluated at every iteration of the experiment. And then the settables are just the frequency and the pulse amplitude. We set them on a grid and we say measure that particular entity. And this is data that we measured using the Impact Consortium as a consortium of different Dutch companies, where we said, hey, let's see if we put our products together, we can build a full stack quantum system to test these kind of things. This is actually data that's about a year old by now, but it just shows that all of this works. And I think also just the little details I always like to highlight is the unit awareness of the labels, the automatic detection of the circular color map when we're talking about phases. But the cool stuff is one we're starting to use is to tune up a transmod. And this is where we're going a bit beyond what Quantifer is, but just showing Quantifer used in action. And I mentioned at the moment that we want to start automating these things, take them to the next level. We need to also start emulating our systems. What I'm showing you here is basically the components of the emulator that's built into part of our software libraries that are not public. But the basic idea is just to show you what components are in there. And I think by having this open source description of what the schedule is, containing all the information of what the signals are that we should apply to the quantum chip, that allows us to emulate this system. So we have here the same hardware abstraction layer we had before, but now instead of putting this to physical hardware, we put it to an emulator. And we have operations, they go into a custom limit equation solver. We have a mock device containing data like the coherence times, but also the Hamiltonian parameters. So we use then SE qubits, a well-known package by now, by the inventor of the transpond, Jens Koch, to get the Hamiltonian model. We have a customly developed limit equation solver. From this, we get Pauli transfer matrices for our operations. The schedulables, which are part of the schedule, contain all the timing information. These two combined go into a quantum sim, a density matrix-based circuit simulator, for which we get populations, and then we put in a readout module to give us back the measured signals in volt. And this allows us to run identical code on the real setup as well as on our emulator. Now, I cannot give you a live demo of a real setup, but I can give you right now showing all of this in action using our emulator. And I think that is just very, very cool. So I'll be giving you a demo on how to tune up a transpond qubit. And let's go do it. So let's go here. Again, we have here a user guide explaining the basic concept about what the abstraction are, what measurement functions are, what calibration functions are, how you could use this to make your own custom experiments. And I want to show you tutorial number 2. And like before, I have prepared this and ran all the examples before we went into the meeting to ensure everything runs. Just restarting the notebook and connecting to everything. But what we're seeing here is basically, it's not just that we're putting the code snippets here, but we're really explaining here to the level that hopefully a master student can follow with the right, here's my visualization popping up. I ran the cells on the side. We see all the instruments being connected and an experiment running. I'll hide it so I can talk about this first. We see here a quantum device, a device element. There's a review paper that I was a co-author of that we published last year, explaining how to set up the basics for superconducting qubit measurements. This is how we connect to the setup. This is always the same, except in this context, initialization is for the mock setup and not for the real setup. And basically, the starting point for finding any qubit is always to finding the readout resonators. And in this case, we're also doing that. We're running a spectroscopy experiment using this very simple command. Measurement functions dot spectroscopy, measure heterodyne spectroscopy. I specify my device, which contains all convex, the name of the qubit I want to be measuring, the frequencies, and that should be it. And I just pressed already these commands in my notebook, and we can see here some kind of background signal, some noise, and something. It's a bit of a coarse peak. So the next thing we're going to do is we will be, I think I ran up to here, saying, okay, this is roughly 7.26, but it's still a bit coarse. So now I'm going to rely here. This is my initial guess, and I'm going to run this calibration protocol that should run it and automatically update it. And you'll see here, it ran it zoomed in on this version, and we see one thing. And I can also see now that it automatically, and this is the one of the previous demo here, qubit 0, clock frequencies. These numbers have not been determined yet, but this has now been configured at 7.26007, and that's indeed what we expected to. So you see it's updated it. Also, these figures are stored. I can reproduce them. Now we're going to do the resonator power scan. That one typically takes a bit longer. So I'll just already put them. Then there we have the resonator flux bias scan. So I'll just already start these just so that it's all running. Actually, the simulator is quite quick. So this is a resonator power scan. You see the dispersive shift. Now the key point here is that we're having an emulator, not a simulator. So we only care about qualitatively reproducing the results, because the purpose is really for testing and having the qualitative correspondence. Although it's still a very accurate physics simulator. This is also very cool. This is what happens if we change the flux bias line. You can see here a result. We change the flux bias line and then look at how the resonator shifts, because this is important because we want to make sure that the qubit, the transport qubit, is moved to the sweet spot before we start measuring. And again, here you can also see the power of the persistence mode, because we can see that these data points overlap and these curves make sense. And also we did first a coarse scan, and then we did a finer scan. Based on that, we update the parameters, we set the flux and the qubit frequency. This one takes always a bit longer to simulate because at this point, we're now going to do the qubit spectroscopy. And in order to simulate that accurately, we're actually simulating a larger Hamiltonian, because we're also including how the qubit frequencies are shifted based on the qubits we're not driving but are coupled to each other. Because the test device we're using here in the simulator is actually a 5-qubit test device. And there's some really cool details. You can see if the data comes in a second. But since we're doing a full limlet equation solver and we're using a square pulse, we can actually see sort of the effect of the, you should say, the Fourier transform of our square pulse. That's a bit of an abuse of language, so my apologies for the experts who know what I'm saying. But you can really see here sort of the Fourier transform of a square pulse, so it would look like when you applied it to the Bloch sphere. And that's pretty cool that you can actually see these kind of effects. And now it's almost done. Based on that, we're going to update it. And once we have set the frequency based on this experiment, the next thing that we always want to do is, if you find the qubit, then you want to start running the Rabi experiment. Now, an expert might point out, how do you know so well where to look for the qubit? Relatively, you don't. Well, we put some explanations here as well, sort of on the dispersive shift and also the power-dependent shift and the state-dependent shift. And the thing we measured before was the power-dependent dispersive shift. If you know the coupling strength of the resonator, the qubit, and this is something that's typically fairly standard, fairly well predictable from the designs, you can have a pretty reasonable prediction of where to find the qubit frequency based on this delta parameter. So that's what we're using to have a good initial guess, and that's also why we're moving to the sweet spot where these things are usually close to what you expect in basic room temperature predictions. So we're doing that. Now we're getting to the point that we are running the Rabi oscillation. So let's see, this one takes typically about half a minute to load. Here we see a Rabi. I could go on, there's some really cool things I can do also. This is the coherence measurements, but really show sort of in this all XY experiment that I can change parameters and then you can see them pop up as gate errors. But I believe I'm close to my time limit, which means that I'll go back and go for my conclusion. So to summarize my conclusions, I think that the focus on applications is reflected in the state of quantum software, particularly the open source part. We propose to put Quantifer as a tool in there as a framework to develop hardware agnostic backends and compile into that can be used to do these kind of experiments and development. And in doing so, we propose a novel gate pulse paradigm with explicit timing control that's suitable for qubit tune-up. And although I did not highlight that too much, we're using this on a daily basis to test quantum chips. And because we're also using them to do more advanced things, we're fairly comfortable in that it does at least the basic things very well by now. Another thing, I mentioned a few results from the Impact project. The Impact nanodisk just ended last week, where we ran a multi-qubit quantum algorithm on a 5-qubit quantum device, running a variational quantum algorithm capable of solving differential equations that was developed by Pascal, the Netherlands, one of the quantum companies in Europe. And with that, I would like to thank you all and ask if there's any questions.
Okay, thank Andrea for the very, very nice talk. First, I have one question, because at some point, when you talk about timing control, you add some reference points in your programs, right?
Yes.
They are labels. And then I guess you have some kind of constraints among those labels or reference points. And then how do you solve this kind of constraint? Are you using some kind of solvers for that?
Yeah, so this is a good question. So the assumption that we're making is that people operating at this low level, sort of close to the hardware, but still wanting to use quantum circuits, they're very aware of the timing. So they're effectively manually setting the timings. And the reference points that we support on every operation are start, center, and end.
Yeah.
So you can specify, if I add a new operation, should the reference point of the previous one be start, center, or end? And should the reference point on the operation I add be start, center, or end? The default is that it uses the end of the previous operation and the start of the next one. And then the constraint is that it should be exactly 0 delay. Or you manually specify it. You can say, oh, I want to change the different reference. Like we change it to start, and they start simultaneously. Or you say, I want a specific delay between things. Use cases for this are, for instance, if you're doing an echo experiment, or if you're doing another example is a cryoscope. That's a technique that can be used to sample the effect of distortions. So then you have one pi half pulse, another pi half pulse. They need to be fixed in timing, but whatever you're doing in the middle, that's the thing you're constantly changing. So you don't want the duration of those operations to affect what these other things are doing. Okay. So there's no advanced solver, but it's really, you're specifying explicitly the constraints. In the future, we're thinking of maybe adding also sort of greater than constraints or smaller than constraints. But at the moment, we only support like fixed constraints.
I see. So they are not so complicated. So I mean, so you can just after the compilation, you can generate the absolute, say, timing, right, in your scheduler.
Yes.
Yeah. So for the moment, you have not encountered some complicated scenario where you need to add some more complicated constraints.
No, we have not encountered that. And I think also it's important to limit the scope of what we're trying to do, because we could say we're trying to use this solution as the magical silver bullet for everything in quantum compilation. I think that would be a bad idea. So I like to leave things like circuit optimizations. I think they belong in a higher compilation layer. So we're taking sort of, you have an explicitly written out quantum circuit, but you still might want to have parameterized operations. You want to have some degrees of feedback, like basically everything that you should be able to translate to hardware. That's kind of the space where you want to use something like this. And also, there's of course the language constraints, right? This is being operated at what I would say is the lab scale. So it's mostly about finding out what are the paradigms and the language and interfaces, and putting it like that. Somebody say, hey, now it's becoming complicated or computationally heavy. And at that point, we can say, okay, but we've at least defined very clearly what the interfaces are. And you say, well, let's make a different implementation of this compilation stage. That's not where we are right now, because right now, I think we're still trying to build something that does everything we want.
Okay, good. Any question from the audience?
Yes, can I have a question?
Yeah.
Adriaan. Yes, Adriaan, thanks for your excellent talk. And just now you show a wide range of functionality for measuring qubits. And recently I have had some discussion with superconducting groups in China, like Professor Zhu's group and another group in Zhejiang University. And they all care about the scalability of the control software. And what's your estimation about the scalability of Quantifer? How many qubits can Quantifer support? Do you have any idea about it? And what can we do to improve that?
I think this is an excellent question. And to be honest, I think scalability to the tens or hundreds of qubits, I would not be worried about. Beyond that, you need to seriously think about it in design. And that's what I tried to point out earlier, is right now it's about understanding what should be the interface and abstractions. And we're not yet worrying about decoupling these things. But I believe you also had some excellent suggestions on how we can design the intermediate representation such that we can indeed decouple certain things and parallelize it a bit more. But I absolutely believe that if we are continuing sort of how we compile things right now, we will hit the bottleneck. Because yeah, right now the data structures are very explicit and you can't easily cut it up in pieces. So I think that this scales to the tens to 100 qubits, but not beyond that probably.
Thank you. Yuxin, you have
You're
muted
muted.
yourself.
Yeah. Okay, thank you, Andrea, again, because we were running out of time for this. Thank you again. Yeah, now we have a coffee break, right?
Yes, and 15 minutes.
So let's just stop the recording and then we come back in 15 minutes. We still have 2 minutes.
Yes. But I can start sharing my screen.
Yeah, you can share your screen first, you can test it. Yeah, we can see the screen.
Great.
Okay, I think it's almost the time. So I'm going to have a very brief introduction to Professor Xiang. He's currently an assistant researcher at National University of Defense Technology. Before that, he got a PhD from Delft University of Technology, and he has done some excellent work on executable quantum computing instruction set architectures, EQASM. And because of that work, he received the Micro 50 Best Paper Award and the topics in 2017. And today he's going to talk about a heterogeneous quantum classical programming language and also programming framework. It's called Quingo. So let's just welcome Xiang.
Okay, thank you, Yuxin. Thank you for your introduction. And I'm going to share my understanding on Quingo programming for heterogeneous quantum computing, quantum classical quantum computing. So yeah, it seems the bar is a bit, I don't know how to, can you see my bar here?
Which bar?
Okay, the Zoom control bar. If not, then it's okay.
No,
we cannot see it. We can see the entire screen.
Okay, that's great. Okay, then it's fine. And okay, so I'm going to start my talk. And here today I'm going to give a short talk about heterogeneous quantum classical programming using Quingo. So my talk will consist in several parts. The first part is some basics about quantum computing, and then I will discuss the rationale behind Quingo, and then finally some introduction to Quingo. So why do we use quantum computing? Because it can accelerate some difficult problems for classical computers, like quantum simulation, optimization, machine learning, etc. And so classical beats have two states, 0 and 1. But for a qubit, it can be in a superposition of qubits, 0, alpha 0, kit 0, plus alpha 1, kit 1. So we can donate this state using a 2 vector, alpha 0, alpha 1. And if we have multiple qubit, for example, a 2 qubit state, then we can denote it using a 4-element vector alpha 0 to alpha 3. And actually, for multiple qubits, it can be in a product state, like this one. So in this way, qubits are isolated from the other one. So you can represent the state of 2 qubits using the state of each qubit. And we also have entangled states. So qubits cannot be isolated from the other one, and the state is look like this. You cannot write them into a product state. So if we have n qubits, then we can have a state of 2 to the power of n state, basis state, and this is a huge state space. We also for qubits we have probabilistic measurement. For a single qubit, if we measure it, we have probability p0 to get the state k0, and we have p1 probability to get the state, the result k1. And if we have multiple qubits, for example like this one, and if we want to measure the first qubit, then what we get, we can first rewrite this state into this format, and then we get this measurement result with this probability, and the other outcome is 1, and then we get this resultant state and with this probability. And if we measure one of the 2 qubits which are entangled, then we have a half probability to get 0, 0, and we have half probability to get 0, 1, 1. That's the story. So we have states, and we also have gates. For single qubit gates, it is a rotation on the Bloch sphere, and it can be read like this. So we have commonly used single qubit gates, X, Y, Z, Hadamard. For X gate is a rotation along the it's a pi rotation along the x-axis, and we have Y rotation and the Z rotation. So what's the effect of this rotation? We can mathematically calculate the state evolution using matrix vector multiplication. So if we apply an X gate on a qubit state, alpha 0, alpha 1, and we can get a resultant state alpha 1, alpha 0, like this. This process can be described using matrix vector multiplication. For multiple qubit gate, this is the same, but the matrix becomes 2 to the power of n times 2 to the power of n size. So matrix vector multiplication is the basic element. It's the basic computation element in quantum computing, and this is highly efficient. If we have 2 qubit gate, it's a 4x4 matrix, and we have C0 controlled knot and C phase CZ controlled phase gate, and their matrix is like this. And as we said, matrix vector multiplication is the basic computation element. And if we apply an X gate on 2 qubits, then the state evolves according to this formula, and then we can get a resultant state. Actually, the third and the fourth element exchange their position. And apply a single gate, we can update all 2 to the power of n states simultaneously. This is a highly efficient operation. So we also have universal gate set, like a classical universal gate set, and or NOR. And in quantum universal gate set, a commonly used one is C0, Hadamard, and T. T is a pi over 4 rotation, pi over 8 rotation, pi over 4 rotation along the Z axis. So the power of quantum computing. If we increase the computing resource in classical computer, then the computing power grows linearly as the computational resource. But for quantum, the story is that the computation power grows exponentially as the computation hardware. So huge state space plus highly efficient operations, we can achieve high parallelism, which forms the foundation for exponential speed up. Non-strictly speaking, if we want to double the quantum computing power, we need to add only 1 qubit. That's the story. So how do we express quantum programs? Quantum circuit is the foundation for many algorithms. Circuit model is proposed by David Deutsch in 1989. Deutsch is also the one who proposed quantum Turing machine in 1985, and the circuit model is demonstrated to be equivalent to the quantum Turing machine by Qi Yao in 1993, and the quantum circuit is the foundation of most programming languages. So how do we? What is quantum circuit? Quantum circuit is that we can use such kind of operation is a gate, is a block. Qubit is a line. So single qubit gate is that a block lies on a line. And if we have multiple gates, it is denoted in this symbol. And we also have controlled qubits, controlled gates. Controlled gates is that we can apply a gate on some qubits based on the state of these qubits. So here I show a circuit for teleportation, and this is a combination of multiple gates: hard mod, CNOT, hard mod, and the measurement with controlled X and Z. So the task for expressing a quantum program to express a quantum program, the basic stuff is to express this kind of quantum circuits. But of course, quantum programs contains more than a quantum circuit, because it can also contain quantum classical hybrid computation. So you can use a classical program flow control to direct what you are going to execute on the qubits. So early quantum programming languages. I will talk about the early programming languages using some simple example, just using this teleportation. And scaffold is a very famous programming language proposed by University of Chicago and Princeton University in 2012. And the code looks like this. And the first block describes creating a biostate. This part describes a joint prepare biostate. Actually, it's not followed by a hard mod. And then it also contains some classically controlled X and Z gates. So classical, you can have arbitrary classical quantum interaction here. And the measurement result, sorry. And then the measurement result can be used for classical computation and program flow control. So what's the underlying model of these languages? Is QRAN. QRAN is proposed by Neil in 1996. So classical computer applies operations on qubits, and then the qubits returns measurement results to classical computer, and the classical computer can use this measurement result for program flow control and any other kind of computation. And many languages like Scaffold, QCL, Liquid adopts this computation model. And because QRAM is proposed earlier than any actual quantum architecture implementation, so there is this model has no consideration in hardware constraints. And as a result, there is no guarantee that the program written in this model can be executed by hardware. And if we look at the actual quantum computer, this is the IBM System 1. And if we dig inside it, and then maybe we can see some structure like this, and then there is a chip in the chamber, and it is controlled by some electronics. And finally, we use a PC to control the electronics. So the story is that we have PC, and we have to send the digital waveforms to the classical electronics, and use the electronics to control the qubits. And there is a high latency between the PC and the controller. So the communication has a microsecond latency, which is larger than the coherence time of a qubits, a superconducting qubits. Usually, nowadays, we have qubits of T1 at several hundreds of nanoseconds, but this digital waveform communication requires microseconds. So if you want to send some waveform from PC to the control electronics, then to qubits already decoheres, and the states cannot be maintained. So in this way, the quantum classical interaction is limited at this in this way. It means that if you want to do some classical computation here, the quantum states here cannot be maintained. Actually, in other words, the quantum classical interaction, like here, like the code, this line cannot be implemented. So we depict this model as the restricted heterogeneous quantum classical computing model, and it has a quantum circuit executor. It can execute a fixed circuit, and the communication here, denoted using the gray lines, has a high latency. And so also, if you want to perform some classical computation, the quantum states cannot be maintained. It means that you can use this qubits to perform some computation and then retrieve the states back, the result back, and then do classical computation, and then start the next iteration. But you cannot perform classical computation here when the qubit states are maintained. It can support offline QC interaction, but it forbids real-time QC interaction. This is suitable for most NISQ applications, such as variational quantum eigensolver and other variational quantum algorithms. Some examples include STIRK by Google, Kuiper by Dalhousie, Qiskit and Project Q result binary control. So the Qiskit looks like this and the STIRK like this, but if we look at some radical examples like iterative phase estimation, IPE, then you can see this program. It prepares the qubit state in the eigenstate and then apply phase estimation here. And then it performs the measurement here. And it will use the measurement result CK to calculate the rotation angle theta here. And this calculation happens at real time. Can we support it? And can real hardware support it? The answer is that real hardware can support it, but languages based on restricted HQCC model cannot support it. How hardware support it? And you need to look at the advance in quantum control architecture. For the first generation control architecture, we have AWG and the data collection cards like this, and there's high latency between PC and Zen. And for second generation, actually to use instruction-based waveform generation and measurement. So a distributed system is like this APS system by recent BBM. And another example is the Delft centralized system, Delft. Actually, I developed this block. We use the instruction to coordinate the operation of all electronics and further control the qubits. So hardware, so it is possible for hardware to support programmable real-time feedback using instructions. This is the story. But actually, this is not based on this restricted HQC model. It is based on the, we say this model as the refined HQC model. We use the quantum control processor, replaced the quantum circuit executor. So you can understand the QCP as all electronics are coordinated by the instructions. It can execute quantum classical hybrid instruction program, and it can support real-time classical computation when qubit state is maintained. In this way, you can also support feedback control. And in such kind of system, there are two kinds of QC interaction. The first one is the slow communication, as that in the restricted HQCC, actually using this gray areas, is between the PC and the QCP. And there is also fast interaction between the QCP and qubits. So because the QCP can retrieve qubit result at hundreds of nanoseconds time scale, so it is possible for the QCP to control the following operations. Some QPL programming language example includes Opaque, Q-sharp, SQRR, and also the ECASM plus OpenQL. The question is that Q-sharp, Opaque, SQRR are sufficient or not? My answer is not, because, for example, Opaque and OpenQL, they have very complex syntax and not comprehensive enough. For example, if you look at this piece of program, you can hardly recognize the program structure here, but actually you can write the same program using this code, which is more structured and more transparent what it is doing here. So, and Q-sharp, its goal is towards large scale fault-tolerant quantum computing. So it has almost no consideration for NISQ devices. For example, timing control, opaque operations. I'm going to introduce it later. So our proposal is Quingo. Quingo stand is short for quantum lingo. You can look like this. And actually it has two different meanings. The first one is it is a system designed to integrate and manage quantum classical software and hardware. So because if we want to do quantum and classical hybrid computation, we need to organize the hardware at first and then organize the software later. So the Quingo framework is a system design not only for the software but also for the hardware. This is the first meaning of Quingo. The second one is that it is a language. This language describes the computation happens on the quantum coprocessor. So it has nothing to do with the computation on the classical host, but only on the quantum coprocessor. So Quingo framework looks like this. First, qubits are controlled by some control electronics. Here I denoted it using quantum control processor to show that this stuff is controlled by instructions. And if we don't have software hardware here, actually we can use software to simulate them. We can have a control architecture simulator to simulate the behavior of control processor. And we also have qubit simulator to simulate the qubits. And then we have classical processor CPU, and which can be replaced by supercomputer clusters, etc. On top of they are communicated using Ethernet, DRAM, or any other way as you like or as you can. And the program, the quantum kernel describes what's happening here, and the host program using Python or Julia describes what's happening here. And the quantum compiler compiles the program and with parameters provided by the host program. with the help of the control software like Quantifer, we can transform the program into a format executable by the hardware. And finally, we have a runtime system to integrate both parts and to interact with both hardware. That's the idea behind the Quingo runtime system. Let's have a simple example. Look at a simple example. This is a quantum random number generator example. It contains two parts. The left part is a Python code, and the right part is the Quingo part. So why two languages? Because the classical parts runs on the classical computer, and this part runs on the quantum coprocessor. So in this case, we are very easy to describe real-time quantum classical interaction here, because any quantum classical interaction written here will actually happens on the quantum coprocessor at real time. Second, this because the compiler only accepts the code happens runs on the quantum coprocessor. It makes optimization much easier.
Hello? Xiang, can you hear us? Oh, he's lost. I guess we need to wait for a moment. Wait a minute, I'm going to call him. Okay, so Xiang is reconnecting. Just wait a moment.
Sorry, I got lost just now. So
Yeah, it's okay
how
now.
many? Yeah, how many minutes do I get lost? And on which page?
Maybe 3 minutes.
And have you seen this page?
No. You should share your screen.
Oh yeah, that's true. Sorry. So have you seen this page?
Yeah. We are in this page. Yeah.
And this page?
We have seen this.
You have also seen this, yes?
Yeah.
And this one?
Yeah, again, we have seen that.
And then this one? Okay.
Yeah,
Nope.
you're talking about this one. Yeah.
Yeah. Actually, I get lost here. That's the story. Okay.
Yeah.
So, and Quingo, a framework designed a quantum program lifecycle, and it contains 6 phases: editing, classical compilation, classical pre-execution, quantum compilation, quantum execution, and classical post-execution. So the story to devise such kind of program lifecycle is to help us to understand how quantum part and the classical part interacts. So and the different stages can contribute to a modular system design. This is the idea for that. So the first stage is editing. You write the program using your favorite language, for example, Python and Quingo. So the left side is for the classical part, and the right part is for the quantum one. And we execute, and then you need to perform classical compilation. For interpreted languages such as Python, you may don't require this phase, and you can directly execute them. And after classical compilation, and then we go to the classical pre-execution phase. So this code actually runs on the classical CPU, and then when we execute to this line, it will say, okay, call Quingo. It means that we are going to start our quantum execution. So before quantum execution, we need to compile the quantum program. And then this happens quantum compilation here. And then the code is compiled into some format accepted by this one, by the quantum coprocessor. So you can start to run it. And then the quantum program runs on the quantum coprocessor. After it finishes execution, the result is returned to the classical CPU, to the host CPU, and the host CPU accepts this result and continues the following computation. Here I do nothing, I just print it. For other cases like VQE or VQA, you can use the measurement result to do some post computation. For example, some search for the next round parameters. And there is a question: why do we do classic quantum compilation just before the quantum execution instead of do quantum compilation before the entire execution? The reason for that is that because at this moment we do compilation, all the classical parameters can be determined, and such kind of information is very helpful for optimization during the compilation stage. So we do quantum compilation immediately before the execution phase. This enables a bigger optimization space. So we are, in order to manage the phase and the program life cycles, we need to have a runtime system, and it looks like this. And everything inside this module is inside this system is a modular system, and you can replace them each module with any other implementation. So, and the phase manager forms the core for the runtime system. So, okay, so let's have a look at the Quingo program design. And you can simply install Quingo using pip install Quingo, and this one we are install the runtime system for you, and then Python Quingo install Quingo C, and Python -m Quingo dot install Quingo C, then we will install the Quingo compiler for you. And so the idea, the system will look like this. Overview: Quingo is a strong typed languages. It has three new types: qubit type, timer type, and time type. Qubit type used to denote an object is a qubit. Timer type and time type are dedicated for timing control in the Quingo languages. And we also have some classical types like bool, int, integer, double. Actually, this is float, and this is none, because this is especially used for a function return type. And we also have array tuple function. So this is Quingo is an imperative language. It has some expressions. It's all from this is borrowed from C languages. So if you are familiar with C or C++, you are very easy to understand the meaning of them. And we also have for some very common statements: if, for, while, return, break, continue, etc. Also, how do you allocate a qubit and release a qubit? We need to use the using statement. The using statement forms the only way to allocate a qubit. And we also have opaque operations, because in some experiment, because in quantum experiments, for example, to calibrate qubits, we may use operations that does not have clear, well-defined. This does not have well-defined quantum semantics. It might be just simply a waveform. So we use operation to represent them. This can be low level and hardware primitive. And we also have timing control mechanisms to specify the relative timing relationship of operations. This is to support quantum experiments. Let's look at a quantum hello world example, the quantum random number generator. So first, we define the opaque operation here. Opaque operation, you see, this is it starts by a keyword. opaque, and then followed by its name and its parameter list and its return type. And it can be a hardware primitive operations, and its meaning is defined outside this program. And when you switch this implementation from one system to another system, you simply replace the configuration file for this operation. And this is an example for the configuration. So it's based on JSON, and it specifies the meaning of an opaque operation here. And you can also have function declaration, operation, quantum random, QRNG, and this parameter, it accepts no parameter, and it returns a single Boolean value. And so here you can also declare an operation without its body. So and then this operation can be defined at some other file. And we can here it's an example for declare a variable. So it consists of a type, a name, and an initial value. Of course, this initial value can be optional. And you can use using statement to allocate qubit. Actually, using is the only way to allocate qubit. And you can allocate a qubit array, or qubit tuple. Qubits are only valid inside this block. When you go out of this block, and you cannot use Q anymore because it's no longer alive. And Quingo automatically releases this qubit when leaving this block. And okay, this is an example for calling another operation. So, and it returns a value here. So at last, I'm going to show some simple demo with Quingo. And here here I have already installed my Quingo environment. If not, I can show you. As you can see, I have already installed Quingo 0.1.6. This directory contains several simple examples for Quingo program. And if we look at this first example, this is an example for running a bell state. Oh, where is my program? Yes, this one. And the full program contains two parts, the left side and on the right side. The left side is the host Python program. It runs on your classic computer. So the basic, you import the Quingo interface, and then you are going to use some methods provided by this interface, like call Quingo to call this quantum kernel to do something. And here is the logic you do. So how do you call the Quingo kernel? Is that you provide the file, okay, which file specifies the operation and which operation you are going to call. Because this one accepts no parameters, so there is no trailing parameters here, and this performs the call. And when you call this one, okay, if it fails to call, then it returns false. Otherwise, it returns true. And upon a true return, this program will print the returned value here. And I can show you some detail here. So I'm going to go to that. Okay. So how do you run the entire program? The story is that you simply Python host program, and then it starts to execute. So it connects to a backend. For now, the backend is the simulator developed by us, and then it calls this one. Okay, connects to this backend, and then execute this code. And when this code is called, it is connected to the runtime system. The runtime system will trigger the compilation of this one, and then starts to execution. If we look at the verbose information here, we can show this process. It connects to the backend, and it connected. and then it starts classical computation, and then it starts quantum compilation. And this quantum compilation finishes, it generates the QCRS program. This is the quantum control instruction set developed by Professor Zhu's group. And then the compiler executed, and then the file is generated, and then this program is uploaded to the simulator for execution. And after the simulation finishes, it returns the result back to the host program, and then we can dump the final state. So we can say we can retry and we get 0, 0, and 1, 1 in this way. And this is a simple program. And then we can see a program with some parameter. Let's look at the Ghc one, Ghc example. The Ghc example is one here. And something different here is that it accepts a parameter. How do we pass the parameter here? We can simply put the parameter here, and the runtime system will convert the parameter in Python language into Quingo language. It is done automatically by the runtime system. And also, if we want to execute it, we can execute it in the same way. So simply, I'm going to show something different. So first, execute it, and then it's connected to the backend, starts quantum compilation, and generates the instructions, and then upload it and execute it, and then returns the result. And here, it generates a build directory here. And if we look inside it, and it has some intermediate. This is instructions generated by the by this program, and then there is a main program. This is a compilation intermediate file, and this one is actually used by the compiler. So this one, after this one is generated, it is simulated by the compiler. So, and we are going to look at the Quingo can be run on your own computer. It can also be run on the quantum computing cloud platform. This one is the address is quantumcomputer.ac.cm. This one, and if you look inside it, it will connect to you can use some real hardware to do some computation. For example, I'm going to create some new experiment here. And okay, ESWEEK. And I'm going to use. So you will see a page here, and then you can select which language you are going to use. Oh yes, here I can choose Quingo, use Quingo, and then I'm going to load some program here, and then the program is loaded here, and then I'm going to compile it. After the compilation succeeds, it will print the quantum circuit here, and then we can run it. Okay, after okay, I run it, and then this is submitted, and we need to wait for some time to see the result. Okay, it's operating. Let's see how much time we need to wait. Okay, so the result is already available here. So we can see the result here. You see, we see most states is 0, 0, and 1, 1. And also because of the noise, there are some other measurements. So that's the basic idea of using Quingo. And there are limited by time. I'm not going to show more demo here. So the story there is more about Quingo. For example, quantum classical heterogeneous programming, and quantum classical co-optimization and timing control. And if you are interested in this, you can go to the you can search Quingo online, and then find the Quingo very easily. If you search Quingo, and then okay, plus quantum, and then you will see the homepage of Quingo. and then you can find more information here. This is a documentation for Kringle. So thank you all.
Okay, thanks, Xiang, for the very basic and very nice talk. Since we are running out of time, maybe we can pick one quick question if someone has a question. If there's no question, okay, thanks for Xiang again.
Yeah.
Then we move to the last talk. It will be given by Lingling Lao. Okay, I'm going to have a very short introduction to Lingling. She's currently she's I think associate professor at Northwestern Polytechnic University, and previously he got her PhD. She got her PhD at Delft University of Technology again. This is the third one right today to this session. After that, she worked as a research fellow at University College London. And now, okay, let's just welcome Lingling for her talk about quantum compilation. Okay.
Oops. Cannot see my screen.
Yeah, we can see your screen.
I cannot see my slides. Okay, yeah. Can you see my slides?
Yeah.
Okay, great. Okay. Oh. But you're seeing the presenter view, not the audience view, right?
Yeah, this is in the correct format, yeah.
Oh, okay, all right. Yeah, thanks for the introduction, and also thanks for joining this session. My name is Lingling from Northwestern Polytechnic University. So today I'm going to talk about quantum compilation for near-term quantum computers. And in this talk, I will first introduce what is quantum compilation, and then introduce the general purpose compilers. Afterwards, I will discuss two special compilers, which are the noise-aware compilers and the application-specific compilers, and finally summarize this talk. So this is the full system stack of quantum computers, and our goal is to implement some quantum algorithms, for example, quantum simulation algorithms, short factoring algorithms on the real quantum chip, such as superconducting qubits, quantum dots, or trapped ions. And this implementation requires different layers. First, we need to describe our quantum algorithms by using some high-level programming languages. And then we will use a quantum compiler to compile these high-level quantum circuits into a set of, a series of instructions that belong to the quantum instruction set architecture. And the microcontroller architecture will translate each instruction into the proper signals that will be finally applied on the real quantum hardware. And now we know we are entering the NISQ area, and current quantum systems have around 100 qubits. And however, for practical applications, for example, for the QAOA circuits, it requires around more than 1,000 qubits. Therefore, there is a huge gap between algorithm resource requirements and hardware that is available right now. And furthermore, the NISQ devices have many hardware restrictions. For example, it has limited gate size, and we know that most of quantum processors support only single qubit rotations with one or a few 2-qubit gates. For example, the Google Sigma device supports the Sigma gate, square swap gate, the CZ gate. The IBM Montreal device allows CNOT gate. and the Rigetti husband device supports a swap gate and a CZ gate. And moreover, these devices have limited qubit connectivity, meaning that we can only perform 2 qubit gates on the connected qubits. And besides, these devices are quite noisy. For superconducting qubits, the coherence time is around tens of microseconds, and the 2 qubit gate fidelity is around 99.5%. And this noise also vary across qubits and gates. So the question is, how can we execute quantum, how can we execute our quantum algorithms that is hardware agnostic onto the real quantum devices which have many hardware limitations? The answer is gonna use a quantum compiler. So what is quantum compilation? I will just quote the definition from this paper. Compilers are software programs that translate an algorithm written in a high-level programming language into machine language instructions that can be executed step by step on particular hardware. And compilers also perform code analysis and optimizations to identify more efficient mappings on the targeted hardware. And in this talk, by quantum compilers, I mean that we want to perform mappings such that we can map our quantum algorithm on the targeted hardware. And also we want to perform optimizations to optimize circuits such that we can achieve higher fidelity. And this is a framework of one general purpose quantum compiler. It consists of several compilation passes, and then it will compile a device agnostic quantum circuit into one that is executable and optimized. So first, it has gate decomposition and optimization paths, which will decompose the input circuit into the hardware gate site. And it also optimizes these circuits to minimize the number of gates. And it also has qubit initial placement and qubit routing passes such that it can place qubits close to each other and try to reduce the number of swap gates that will be used for non-nearest neighbor 2 qubit gates. And the reason we want to minimize the number of gates or the number of 2 qubit gates is because we know that we have quite high 2 qubit gate errors in the NISQ devices. And also because of the decoherence limitation, we also want to perform gate scheduling to minimize the circuit depth or the circuit runtime. There are many general purpose compilers have been developed. For example, the Qiskit compiler from IBM, TKit compiler from Cambridge Quantum, Cirq compiler from Google, QSharp from Microsoft, Quark from Rigetti. And all these compilers have these 4 different compilation passes, and they may also have more advanced optimization techniques, and also maybe they organize different passes in different orders. So here we will show one compilation example and to go through every compilation steps. So here, first we have the gate decomposition procedure. For example, if we want to decompose a QAOA application, and this shows the QAOA application operation, which is a 2 qubit ZZ interaction. And we will have to decompose it into the native 2 qubit gate set. For example, if our native 2 qubit gate is CZ gate, then we can decompose this unitary in this small or sub-circuit, which has 2 CZ gates. And if our native hardware gate is a swap, square root I swap gate, we can perform such a decomposition that requires 3 square root I swap gates. And afterwards, we will map the decomposed circuit on the connectivity limited hardware. For example, for this example circuit, we want to map this circuit onto this 3x3 grid architecture. And we will first perform a qubit initial placement that will try to place qubits that will interact close to each other such that we could reduce the number of swap gates in the later session. And then with such an initial placement, we can see that for the first 3 cycles, all the 2 qubit gates are nearest neighbors, so we could directly implement them. But for the gates in the 4th cycle, these 2 gates cannot be implemented because qubit 0, 5 are not neighbors and 2 and 3 are not neighbors. Therefore, we will need a routing procedure to route qubits to be neighbors. And the routing operation could be implemented by the swap gates. So here we can insert 4 swap gates to perform this, the rest of the CNOT gates. And after the routing, we also need to schedule the operations to explore the maximum parallelism such that we can minimize the circuit depths to mitigate the effect of decoherence. Now we have a sense of quantum compilers. So we have introduced the general purpose compilers. It considers the gate size, the topology, and the decoherence and gate error effects. However, these compilers haven't considered the noise variations in our current devices. For example, on the IBM Montreal device, we can see that different qubits have different coherence time. And also, the gates on different qubits have different error rates, as shown in this heat map. And also, when performing multiple 2 qubit gates on parallel, there could be crosstalk errors. That is, one gate could introduce errors on the other gate. So in order to further suppress this or mitigate these errors, some noise-aware techniques have been proposed. For example, we can decompose gates into the most reliable native 2 qubit gate if there are several native 2 qubit gates. And we can also map our circuit qubits to the most reliable area on our device. We can also route qubits by choosing a path where all the qubits have longer coherence time. We can also leverage the decoherence effect with the crosstalk errors. We know that for decoherence, we want to minimize circuit depth, so we want to perform more parallelism. But for crosstalk errors, we want to perform some gates sequentially rather than parallel. So we have to leverage this by performing some special schedulings rather than the general schedulings. In this talk, I will use the noise-aware decomposition as an example. So here we assume that we could have several 2 qubit gate types, and 2 qubit gates are very important. They have a significant influence on the instruction counts, and different 2 qubit gates are advantageous to different applications. For example, we know for quantum error correction, we would use CNOT gates, and for quantum chemistry, and FSIM gate family is quite advantage. And also for optimization, like QAOA, the safest gate family is also very useful. And offering multiple 2 qubit gate types can cater to different applications, and this will reduce the instruction count and in turn improve the application fidelity. And current vendors have proposed some continuous gate types. For example, Google have this FSIM gate family. and Rigetti has proposed this XY gate family. So with multiple 2-qubit gates available, we can use a noise-aware decomposition. It considers the gate fidelity variations across gates and also qubits. So here, assume we want to implement a target unitary UT, so we need to decompose this. And the decomposed unitary could be the UD. And we define the decomposition fidelity by the Hilbert-Schmidt inner product. And this is the decomposition fidelity. And we also define a hardware fidelity, which is the hardware fidelity product of all the gates in our decomposed version. And then we finally define the implementation fidelity of our target unitary, which is the product of the decomposition fidelity and the hardware fidelity. And here, we know that in current quantum hardware or even in the near future quantum devices, the gate error rates are normally quite high. So the hardware fidelity is quite low. And in order to improve the implementation fidelity, we could leverage the decomposition fidelity with the hardware error rates. So that is, with an exact decomposition, we may require many native 2-qubit gates, but they have quite high error rates. So in order to improve fidelity, we could have an approximate decomposition, which requires fewer native gates. In that sense, we will increase the hardware fidelity and the overall implementation fidelity is increased. And furthermore, on current devices, the noise also vary across gate types and different qubit pairs. So we could select the best gate on each qubit pair. Let's use this example. So we want to decompose this SU4 unitary into either a CZ gate or either XY gate. So for CZ gate side, we need 3 CZ gates, and we also need 3 XY gates for the exact decomposition. And if we want to implement this small circuit on this Rigetti's Adband device, and we can perform either the exact decomposition as above circuit, or we can perform a noise-aware decomposition, which will first consider the first unitary on qubit 2 and 3, as we can see here. So as you can see, the CZ gate on this qubit pair has higher fidelity than the XY gate. So the noise-aware compiler will choose the CZ gate as its native 2-qubit gate. And also, instead of having an exact decomposition which requires 3 CZ gates, it uses an approximate decomposition that requires 1 CZ gate. That is, leverage the hardware error rate with the decomposition fidelity, and therefore the overall implementation of this, the first unitary, is increased. And similarly, for the second unitary on qubit 3 and 4, it also chooses XY unit gate as its native 2-qubit gate, and also performs an approximate decomposition. So from the evaluation results on Google's Sigma device, we can observe that. So this is a quantum volume benchmark, and we compare the noise-aware decomposition called NUOP here with the exact decomposition in Google Circ compiler. And as you can see, the noise-aware decomposition improves application fidelity for all the circuit size. And also, so for example, for this 2-qubit example, it doubles the quantum volume. And moreover, if we look at the noise-aware decomposition results, you can see that the decomposition with several 2-qubit gates, for example, the light blue bars, it has higher fidelity than the gate set that only has one single 2-qubit gate type. So this means with multiple 2-qubit gate types in our gate set, we can reduce instruction count and improve application fidelity. However, there is a problem with multiple 2-qubit gate types. That is, we will have higher calibration overhead. For example, for Google's Sigma device, it takes around 4 hours per day to calibrate all the single qubit and 2-qubit gates. So it's very expensive. Therefore, there's a trade-off between the number between the expressivity and also the calibration overhead. And we can also use this noise-aware compiler to study these trade-offs. For example, we could assume a set of applications and then assume some configurable instruction sets as FSIM gate sets or the XY gate sets, and use the noise-aware decomposition method, and then run simulations based on the real noise parameters or on the real devices, and also assume the available calibration model based on current systems to study the trade-offs between the application expressivity and also the calibration overhead. And we have done this on Google Sigma device, and we have some very interesting observations. So as you can see from the left figure and also the right figure, the calibration overhead increases with the number of 2-qubit gates, and the expressivity of the reliability, as shown in the right figure, improve with the number of 2-qubit gate types. And interestingly, we have some sweet spots. That is, if we have around 4 to 8 gates available, they could provide sufficiently high reliability and relatively low calibration overhead. So now we have learned general purpose compilers and noise-aware compilers. Both compilers, they work at the gate level, and they do not exploit the application level properties. For example, for the QAOA circuits, as shown in this figure, all the 2-qubit interactions are commutable. So that is, the order of these commuting gates are is flexible, and we can reschedule all these gates to reduce the number of swap gates and the circuit depth. However, this is complicated or difficult to be exploited in the general purpose compilers. And also for the VQE application, it has many poly gauges, and the poly gauges, they can be decomposed in different ways, as shown in this figure. So it is flexible to choose efficient decomposition for different mappings if we have, connectivity limited device, because each decomposition requires different connectivity. And if we have the freedom to choose, then we could optimize the circuit and minimize the number of swap gates. And for quantum simulation based on trauterization, we can also perform some application-specific optimizations, because for this application, there are many non-commuting terms. So mathematically, they are not commutable. And for the general purpose compiler, we could not change their orders, because the general purpose compiler always respect the gate dependency. But at the application level, based on trautorization, we could actually randomize these terms. So the order of these non-commuting terms is flexible, and we could exploit. And here we will use the Toucan compiler as an example. It is designed for 2-qubit Hamiltonian simulation algorithms. And the left figure shows the example circuit where all the control circles as 2-qubit interactions in the Hamiltonian. And those gates may not be commutable. And the Toucan compiler consists of some general compilation passes and also some application-specific passes. In particular, the qubit mapping pass is not application-specific, so we could use the initial mapping algorithms from the general-purpose compilers. And the qubit routing procedure is application-specific. So as I have mentioned many times, so for the general purpose compiler, it always respects the gate dependency that appearing in the input circuit. So, but for the quantum 2-qubit Hamiltonian simulation algorithms, all the terms could be reordered. So we could randomize these terms. And then in the routing pass, that means there is no gate dependency for these interactions. And given a qubit initial placement, we could schedule out the nearest neighbor gates first on the initial qubit mapping, and then insert swap gates for the non-nearest neighbor ones. For example, given this circuit and also this 2x3 qubit architecture, and we can perform such an initial placement, and the general purpose compiler always respect the gate dependencies appearing in this input circuit. That is, it will schedule and route each 2-qubit interactions one by one in this circuit, and eventually it requires 3 swap gates, and this compiled circuit has depth 7. But our application-specific routing technique is designed in the Toucan compiler. We'll notice that, we could randomize all the 2-qubit gates. So that is, even with the same initial placement, we could reorder all the 2-qubit gates. And first, we choose all the nearest neighbor gates. As you can see, the orange gate in this circuit is actually located in the last cycle in the input circuit, but we could change their orders. And by doing this, we only require 2 swap gates, and the compiled circuit has depth 5. So after routing, we will also perform gate optimizations that could merge a swap gate with a circuit gate. For example, in this circuit, the control circles are the circuit gates we have in our input circuit, and this is a swap gate. And if the swap gate and the circuit gate, they are applied on the same qubit pair, then we could move the circuit gate and unify it with the swap gate. In that sense, we will reduce the number of native 2-qubit gates in the decomposition. So this will help us to minimize the circuit size. We can do this only if we know this permutation property of the flexibility of reordering of the circuit gates. And after the gate optimization, we also perform gate scheduling, which is also application specific. And in particular, again, we have mentioned many times the general purpose compiler always respect the gate dependency, but in our case, there is no gate dependency among the circuit gates, but there is a dependency between a swap gate and the circuit gates that need to be routed by these swap gates. So it's a hybrid scheduling. There's dependency between swap gate and circuit gates. There's no dependency between circuit gates. And we perform a heuristic optimization, and it scales quadratically as a number of 2-qubit gates. And so, for example, for this circuit, the circuit compiled by the general purpose compiler takes 4 cycles, but with this application-specific scheduling, the compiled circuit has only 3 cycles. So after the scheduling, we will also perform gate decomposition and optimization. And because this, as you see in the very early slide for the general purpose compiler, we normally perform the decomposition before the qubit placement and routing and scheduling. But for this application, we perform decomposition after the scheduling such that we could target different gate sites. And then we evaluate this Toucan compiler by running the QAOA application on the real on the IBM Montreal device. So as you can see from these 3 figures, so the first figure shows the 1-layer QAOA, and second is 2-layer QAOA, and 3rd-layer QAOA. And as we know that theoretically, as you can see from the blue lines, theoretically, if we increase the number of layers, the performance also is improved for the QAOA application. But in reality, we know that if we increase the number of layers, that means we will increase the circuit depth and introducing more errors in our circuits, and the performance could be compromised. This is common, and we can also observe this for the other compilers, as you can see here. But with our Toucan compiler, we can see that for this 4-qubit application, our Toucan compiler could improve the performance when increasing the number of layers, and also compared to the Ghc compiler from IBM, the TK compiler from Cambridge Quantum, and also the QAOA compiler from another group, sorry. And then our Toucan compiler achieves the highest performance for all the problem sizes. So to summarize here, compiler techniques are necessary for mapping hardware agnostic quantum applications to near-term quantum computers. And we have learned general purpose compilers. They can target different quantum algorithms and different quantum technologies. And normally their goal is to minimize the number of 2-qubit gates or the circuit depths in order to mitigate the effect of gate errors and decoherence. And noise-aware compilers could further mitigate errors by exploiting the noise variations across qubits and also across gates. And therefore, they could further improve the application fidelity. And then we also introduced the application-specific compilers. They only target some special applications, but they could exploit the application properties and perform more optimizations to further reduce compilation overhead and improve the application fidelity. And these compilers are very popular in the near-term quantum computers as we are using right now. But however, for the long term, we will have to perform fault-tolerant quantum computation. In that sense, we will also need different compilers, that is, fault-tolerant compilers for different quantum error correction codes. So this is the summary of all the quantum compilers based on time. So at the beginning, we have all the general purpose compilers, and then as we are entering the NISQ area, we have some NISQ compilers, including the noise-aware compilers and application-specific compilers. And for the long term, we will design fault-tolerant compilers, and also some error correction-specific compilers, and maybe some other optimizations will be performed between the NISQ area and the fault-tolerant area. And thank you for your attention.
Okay, thank you, Lingling, for the wonderful talk. So we have some time for questions. Actually, I have one question. We have a message first. We have a message from the audience. He says, I have a question about the quantum noise. Are quantum computers easier to produce noise than classic computers, and why? Can the noise be eliminated by some technologies? That's a question from Yu Hong Song.
Hi, thanks for the question. It's a very good question. So yes, so quantum computers are very noisy compared to classical computers. And as we know, for classical computers, for example, for the CMOS, it has error rates around, let's say, 10 to the minus even 20. But for current quantum hardware, because of the law of quantum mechanics, so qubits are very, decoherence all the time. And our gate errors is around 10 to the minus 3. So it's relative, much higher than classical computers. And it's very difficult to eliminate it by the current by technologies, because they will be decoherencing and we will not be able to eliminate this. We can just try to extend the coherence time, try to improve the gate fidelity. But because of this, people have developed some quantum error correction techniques, error correction to suppress errors. In principle, it could suppress errors exponentially. So for the long term, that is what I said in the last sentence, we will need fault-tolerant quantum computation and fault-tolerant quantum compilers.
Okay. I have a question concerning the application-specific compiler. In order to make use of this kind of application-specific compilers, you take advantage of some very special properties. Say some quantum gates, they can commute with each other, right? Then you record the gates. But this looks like very advanced knowledge. So how do you first how to observe to get this kind of knowledge, and then in the case you have this knowledge, how do you say let the compiler know that? Say, are you putting some kind of rules to say, this kind of circuits can be exchanged and you can rewrite the circuits?
Yeah, so it's it's an excellent question. So we have to know what are the new properties for this application. And as I mentioned, for the QAOE circuit, so all the 2 qubit gates, they are commutable. Mathematically, they are commutable. And then in principle, the compiler could learn this, could compute the matrix multiplication and know they are commutable and perform optimizations. But computing this, perform this matrix multiplication will be very expensive. So, and it will slow down the compiler. And if we have an application specific compiler, knowing that, so knowing these rules, okay, so for these circuits, we know all the gates are commutable. We could change their orders, and it's very easy to perform the compilation, and it will be very fast. And for other applications, as I introduced for the quantum simulation, the gates are not commutable mathematically, but at the higher level, at the application level, when we perform trautorization, the order is not, let's say, determined. We have the freedom to choose the orders, but in general, the general purpose compiler will always assume the order appearing in the input circuit. But this is not the case. So that's the reason why we are designing this application specific compilers. So as you said, we need to define some rules for this new type of compilers. Mm-hmm. And this cannot be generalized to the other applications. This is like kind of the drawbacks of this type of compilers, but it will improve the application fidelity.
Okay, I see. Okay, thanks. Any other questions from the attendees? No. Okay, so if there's no question, let's thank Lingling again, and also we thank all the 4 speakers for the afternoon session. And then that.
Thank you for organization.
We can conclude the tutorials, right? Xiang, do you have anything to say?
I think this is. I think today's. If I would like to, if let me to conclude this session, I would say, okay, this tutorial covers 4 topics regarding related to quantum control, the hardware implementation, the quantum control software, compilation, and the programming language. It covers the most important aspects of a full-stack quantum computer. And I hope in the future we could have more collaboration across different stacks, from the programming language, compiler, control software, and the actual hardware. Originally I worked in Delft, and I worked with Adriaan for control to develop some control stuff for superconducting qubits. I developed the control electronics, and he is devoted to the control software and use them to perform some experiments. And I hope in the future we can have more opportunity to have this collaboration. And this day, what has changed is that when I started in Delft in 2014, superconducting technology in China is not as advanced as that in Europe. And nowadays there are many larger chips in China, and groups like Professor Zhu's group is confronted with many control problems that are quite new. So I think such kind of collaboration would help each other. This is what I would like to say.
Okay.
Yeah.
That's wonderful observation. Yeah, we hope to have more, say, collaboration, and also maybe say in the next, I don't know, maybe for ESWEEK 2023. I don't know if have more opportunity to organize another tutorials. And let's see.
Yeah.
Anyway, let's thank the speakers and also thank the all the participants. Okay, for the tutorials. Okay, thanks. And then
thank you all.
Thanks for the organization. Thanks for joining.
Yeah.
Thanks for joining. Bye-bye.
Bye.